Hello, and welcome to Chemistry with Dr. Clark. The purpose of today's video is to continue our discussion of Hess's law and using it to calculate the enthalpy change for a reaction based on a bunch of given reactions. Now, if you're just looking for a little bit of help with the more advanced problems, then you're probably in the right place. But if you are looking for some help generally with Hess's law, it might be best to take a look at my previous video called Hess's Laws Problems Number 1. Okay, this is Hess's Laws Problems Number 2. So for these problems here, what we'd like to focus on is what happens if you do have a chemical in your target equation that shows up in more than one of your given equations. So the easiest way to do these is to work your way through your target equation, right? This is the equation here that I would like to know the delta H for. So I'm going to call it my target equation. In my target equation, the very first chemical is 4 iron oxides, iron 2 oxides. So if I look for FeO solid through my given equations, I can see that it appears only once. So it's right here as an FeO solid. Now, in order for me to be able to add these two equations together to turn it into the target equation, I need to have the iron 2 oxide in the right place with the right amount. So you can see here I need the iron 2 oxide as a reactant, but in the given equation it is a product. Okay, that's a problem. But we can fix it by taking the equation and flipping it. So what we're going to do is we are going to reverse this equation. Now, as discussed in the previous Hess's law video, if you take a reaction and you reverse it, then you do have to change the sign of your delta H. Think of it like melting versus freezing, right? If you take the entire thing and flip it, then you are doing the opposite process. So instead of putting heat in, heat is coming out. Or instead of taking heat out, you're putting heat in. If you reverse the process, you are going to change the sign for the enthalpy change. So for this one here, because the FeO is on the wrong side of the equation, we are going to flip it. The other issue is the number. In my target equation, I need 4 FeO solids. But in my given equation, there's only 1. But I can fix that as well. All I need to do is multiply everything in this equation by 4. So 4 times, and if you are going to do your reaction with 4 times as much chemical, then you should get 4 times as much enthalpy change. Think of it like a campfire. If you put in 4 times as much wood, then you should get out 4 times as much heat or enthalpy change. Now, this here is jot notes. I've made some notes here on my given equation to indicate what I need to do with it, right? I need to reverse it, and I need to multiply it by 4. Now, I find it's too complicated to try and keep all of this in my mind while I'm working through the rest of the problem. So it works best if once you've decided what you're going to do to the equation, you actually do it. So we're going to flip it and multiply it by 4. So the FeO solid was a product, but now it's a reactant. You had 1 of them, but now you have 4. Okay, if you look at your products, okay, they used to be reactants, but we're going to move them to the product side. And again, we're going to multiply by 4. So it'll be 4 Fe solid. And you used to have, originally, a half of an O2 molecule. If I multiply a half by 4, that gives me 2 O2 gases. Now my delta H, because I have taken the reaction and flipped it, it does go from a negative to a positive. And because I have multiplied everything by 4, I am going to multiply that number by 4 as well. So my 272.0 is going to be multiplied by 4. That'll give me 1088.0 kilojoules. Now, for those of you that don't have to worry about significant figures, you probably would have just written it as 1088. But in the world of significant figures, if you're multiplying this number by 4, you really should keep the same number of decimal places. So that's why I have the 0.0. Think of it like adding. If I had 272 plus 272 plus 272 plus 272, right? Multiplying it by 4 is like adding it 4 times. And if you're adding, you should keep the least number of decimal places. That's why I've kept it as a 0.0. Okay, now we just did a lot of work to get the 4 FeO solids as reactants. So let's put a little blue box around them so that way we can keep track of them. Now, the next thing in my target equation is the O2s. Now, if I come down and look at my given equations, I can see that the O2 shows up in the first equation, but it also shows up in the second equation. When one of your chemicals from your target equation shows up in more than one of your given equations, you really can't use it to figure out what's happening. Okay, oxygens tend to do this, small molecules, Cl2s, F2s, water sometimes. Okay, so for this one here, I'm going to skip using the oxygen. Okay, even though I know that I need some oxygen, because it shows up in more than one of my given equations, I'm just going to ignore it for now and move to the next chemical. What I'm going to do is I'm going to hope that when I add my equations together, the oxygen will just work itself out. Okay, so if we look at the next chemical is Fe2O3. It's an iron 3 oxide. If I look through my given equations, I can see that Fe2O3, the iron 3 oxide, only appears in one equation, right? It only appears here, which is good. Like if I'm going to decide how I'm going to change an equation, the chemical from my target equation can really only show up in one of my given equations. Now, the two things that I need to check. Is it in the right location, and do I have the right amount? Now, location-wise, we're good. The Fe2O3 should be a product, and the Fe2O3 is a product. That's excellent. The number, though, is an issue. I need 2 of them, but I've only got 1. Well, it's not a big problem, because like before, if I want to go from having 1 to 2, I just need to multiply everything by 2. So it'll be 2 times as many irons, 2 times as many oxygens, 2 times as many Fe2O3s, and I'm going to get twice as much enthalpy change. Now again, I do like to write these things out. Like it would be very easy to just make the changes right here on the equation as it's given. But I do like to write them out because especially if you have to flip them, it's very hard to remember what changes you made. So if we rewrite this, I originally had 2 iron solids, so I'm going to multiply that by 2. So that gives me 2 Fe solids. I originally had 1.5 oxygens, but I'm going to multiply it by 2, so that gives me 3 oxygens. And I originally had 1 iron 3 oxide, but I've multiplied it by 2, so now I have 2 Fe2O3 solids. Now for this one, I didn't flip it over, so the delta H started off as a positive, and it's going to stay as a positive, but I did multiply it by 2. So 824.2 times 2 gives me 1,648.4 kilojoules. My K got a little away from me. And again, if you're worried about significant figures, multiplying this by 2 is like adding it to itself. If you add 824.2 to 824.2, you have to keep the least number of decimal places, so you should have 1 decimal place. And again, I worked really hard to get the 2 Fe2O3s in the right place with the right amount, so let's put a little green box around it to highlight that. Now at this point, we are going to add the 2 equations. Because if I can add these 2 equations and they reduce down to my target equation, then the delta H that goes with it is just the sum of the delta H's of the given equations. Now for this one here, anything that shows up as both a reactant and a product will cancel, and I'm not expecting everything outside of a box to cancel, because the blue box with the FeO, that should stay. The green box with the Fe2O3 should also stay. But I also know that some of the oxygens, they also need to stay, right? Not all of my oxygens are going to cancel. So when I look at things that do not have boxes around them, I realize that not all of them are going to go away. Okay, so if we look, this is 4 Fe solids. This is 4 Fe solids. Those two are exactly the same. There's 4 of them. They're both solids. They're both irons. In order to cancel something out, it has to be exactly the same. Okay, so they're gone. If I look at my oxygens, though, I've got 3 oxygen gases on the reactant side. I've got 2 oxygen gases on the product side. They're both gases. They're both O2s. But the numbers don't match. There's 3 versus 2. So they're not going to completely cancel out. What's going to happen is that I'll cancel out 2 of these, and I'm going to cancel out 2 of these. So if you have 3, and you cancel out 2 of them, that should leave you with 1. Which is excellent because I needed 1 O2 as a reactant, and I now have 1 O2 as a reactant left over. Right? So if we write down what's left, here on the reactant side, I have 4 FeO solids. Excellent, that's what I needed. The iron is gone, and 2 out of the 3 oxygens are gone. So I have only 1 O2 gas left. But that's exactly what I wanted. On the product side, the iron solids are gone, the oxygen gases are gone, and I'm left with just the 2 Fe2O3 solid, which again is exactly what I wanted. If the 2 given equations add up to give me my target equation, then the 2 delta H's add up to give me the delta H for this reaction. So if we pull out our calculator, I've got 1088.0 plus 1648.4, and that'll give me a delta H of 2736.4 kilojoules. This enthalpy change goes with this chemical reaction. Now again, if you're talking significant figures, if you're adding something with 1 decimal place to something with 1 decimal place, your answer should have 1 decimal place. Now I believe that in several of the other videos when we talk about Hess's law, or we talk about heats of formation, or we talk about calorimetry, ways of calculating enthalpy changes that go with reactions, the question that comes up sometimes is, why didn't we just do this in a calorimeter, right? Why didn't I just put some iron 2 oxide and oxygen in a calorimeter and directly measure the heat or the enthalpy change that goes with it? For this particular problem here, slowness would be an issue. If you put the iron oxide and oxygen together into your calorimeter, it's potentially a slow reaction. The other issue is that the delta H here is extremely big, but it's also extremely positive. In the world of chemistry, negative delta H's, things that are exothermic, heat is being released, they tend to be spontaneous. They tend to just naturally occur. Things that are positive, things that are endothermic, so heat is being absorbed, very few of those are spontaneous. Very few of them will occur on their own. So there's a decent chance that this reaction out in the real world would either not want to happen or would be very slow to happen. Okay? So sometimes your best way of determining a value for a chemical reaction is through calculation rather than actual experiment. All right, let's try a second one. So for this one here, I've got some fluoromethane, some CH3F. I'm going to react it with 2 fluorine molecules, and I'm going to end up with trifluoromethane and 2 HFs. And what I'd like to know is, what is the delta H that goes with that reaction? Now, there are 3 reactions that have been done. Okay, so this reaction was done and someone measured delta H. This reaction was done, someone measured delta H. This reaction was done and someone measured delta H. And what I'd like to be able to do is add those 3 together to give me this one. Well, let's do what we did the last time. Let's work our way through the different chemicals in the target equation. So if I look for CH3F, so if I look through all of my equations, CH3F only appears in one of them. Okay, there's only one place where you find this chemical. That's excellent. Now the two things that you're going to ask, is it in the right place and do I have the right amount? The amount is good. I needed one of them and I have one. The location is problematic, right? I need it to be a reactant. Unfortunately, it's a product. But we can fix that. All I need to do is take the entire reaction and turn it around. So this first reaction, I'm going to reverse it. And if you reverse or flip a reaction, then you're going to change the sign of the delta H. So it used to be a negative, now it's going to be a positive. Now this is one of those that I really would write out because taking an entire reaction and flipping it around, it's very hard to keep that in your mind, to visualize it as you're working through the rest of the problem. It's one of those things that if you write it down, you have it there and you don't have to worry about trying to remember it. So let's write down our products. So the first product is CH3, F, gas, and the second product was HF, gas. They used to be products, but now they're reactants. If we take our reactants, they become products. So CH4 gas and some F2 gas. Now we didn't multiply the equation by anything, so the number stays the same, but it does change its sign. So it's 433.7 kilojoules. And let's put a nice little blue box around our CH3F. All right. So now if I look to my next chemical, the F2s, I see that I have a bit of a problem. Because F2 shows up in not one equation, not two equations, but all three of the given equations. So really, I can't use this to decide how I'm going to modify any of the given equations, right? Because there's many different ways to come up with two fluorines. You could have like 4 on one side and 2 on the other, and they'd partially cancel. You could have 1 on one side and like 5 on the other side, and whoops, I guess 1 and 3, and they'd partially cancel, right? There's going to be too many different ways to try and possibly modify these equations to give you two fluorine gases. So we're just going to skip them. We'll move on to the next chemical. So the next chemical in my target equation is a CHF3. The only CHF3 in the givens is right here. That's the only place. Now, you need to have it in the right place, and you got to have the right amount. So, I need it to be a product. It is a product. Excellent. I need one of them, and I have one of them. Even more excellent. It turns out that this last equation is written exactly the way I want it. Like, it's perfect. So when I rewrite it, I'm going to rewrite it exactly as it is. CH2, F2 gas, plus an F2 gas, turning into a CHF3 gas and an HF gas. And because I didn't do anything to that equation, I'm just going to write out my delta H exactly as it is, minus 517.4 kilojoules. And let's put a little box around our CHF3. Okay, now if we look up at our given equation, our target equation, the very last chemical is 2 HFs. If I look down through all of my givens, I can see that HF shows up again in every single equation, which means that I cannot use this chemical to determine how to modify any of these reactions, right? If a chemical in your target equation shows up in more than one of your given equations, then you can't use it. Well, now that puts me in kind of a bind, because I have modified the first equation, I have modified the last equation, I really don't know what to do with the middle equation, and there's no more chemicals in my target equation to tell me what to do. So what we're going to do is we're going to leave a space for it, but currently we're going to skip it. what we're going to do is we're going to start canceling, and we're going to hope that the cancellations tell me what I need to do to that last equation. All right, so if I look at this, let's find something that absolutely needs to cancel. Like, I really can't look at the HF because not all of the HFs are supposed to cancel. So that's going to be complicated to look at. I also probably shouldn't look at the F2 because, again, not all of the F2s are supposed to cancel. So that's too hard. But if I look at something like CH2F2, CH2F2 does not appear in the target equation at all. Like, it's not there. Which means that the CH2F2 has to cancel out completely. If I look here on the product side, currently there's not a single CH2F2. So if I want it to cancel, I need to have one CH2F2 gas as a product, right? In order for these two to cancel, if you've got one of them as a reactant, you have to have one as a product. Well, this is what's going to tell me what to do with this last equation. Because that last equation needs to be set up so that you have one of these as a product. So if I come and look at this last equation, I can see that it does have CH2F2 in it. Now, turns out life is good. I needed it to be a product, and it is a product. I needed to have one of them, and there is one of them. So this tells me that this last equation is actually written exactly the way I want it. Okay? So if we do write it out exactly as we have it, CH4 gas plus 2F2 gas turning into my CH2F2, I already have that, plus 2HF gas. And because I didn't do anything to the equation, I don't do anything to my delta H. So that's a minus 921.6 kilojoules. Now, when I cancel, not everything is going to cancel because I really do need some F2s and some HFs left, but a lot of stuff will. So let's work our way through the cancellations. We set it up so that this would cancel. Good. See the CH4 here. If you look at your target equation, there are no CH4s. So this CH4 has to cancel out. If I look on the product side, CH4 gas only appears here. It's a gas and it's a gas. You have one and you have one. That's a perfect match and they cancel. All right, let's talk about our HFs. Here on the reactant side, the only HF you have is there. But if you look on your product side, HF shows up in two spots. You've got one HF here, and you've got two HFs here. Now, because you have them on both sides of the equation, there will be some partial cancellation, right? You've got one here versus 3. 1 plus 2 is 3. So I am going to cancel out one from each side. This one will cancel with this one, but it's going to leave these two. And I'm happy with that because in the end, I'm supposed to have two HFs. Okay, that's good. Now, if we talk about our F2s, there's only a single F2 on the product side, but the F2s show up in two locations on my reactant side, right? There they are. On the product side, you got 1, but on the reactant side, you have 1 plus 2 is 3. So again, you have 3 versus 1. If you have 3 versus 1, let's cancel 1 off of each side, and it leaves 2 here. Right, so this 1 F2 will cancel with one of them here, and it leaves you with this one. Which again is good because I'm supposed to have 2 F2s at the end, and I do have 2 F2s at the end. So now if we actually add up what we have left, I have a CH3F gas, canceled, 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 and I have 2 F2s. And on the product side, canceled, canceled, you have this, CHF3 gas, canceled, canceled, and you have this. So that's 2HF gas. By adding up these 3 equations, I have obtained my target equation. Excellent. And if you can add your equations to get the target, then you can add up your delta H's. So my delta H would be 433.7 plus a negative 517.4 plus a negative 921.6 gives me a negative 1005.3 kilojoules. So if you were to take some fluoromethane, react it with 2 fluorine gases to produce a trifluoromethane and 2 HFs, the amount of enthalpy change, the amount of heat, would be a negative 1005.3 kilojoules. If you're talking significant figures, 1 decimal place, 1 decimal place, 1 decimal place, and therefore my answer has 1 decimal place. All right, let's say we try one more example. So for the last example here, I've got some N2H4. It's going to react with hydrogen gas, and it's going to make 2 ammonias. And I would like to know what is the delta H that goes with it. So at this point, we've done a couple of problems. We have a bit of a routine established, so let's follow our routine. Right? When you're doing problems in chemistry and science in general, it's best to practice them enough that they become routine. You're like, I know what to do step 1, step 2, step 3, step 4. Like, I have a pattern that I follow. Because if you have a pattern, even if the problem becomes difficult, you can still move from one step to the next, because every time you've ever done this, you've always done this first, you've done this second, you've done this third. So for these problems, I always take a look at the chemicals in my target equation. Start at the beginning, work your way across. So if I come down here and look at my 3 given equations, N2H4 liquid, I can see that it only appears once here. And it's very good if the chemical that you're looking for only appears in one formula. Because if it only appears in one formula, that allows you to modify that formula, right? If it shows up in more than one, then you can't use it. Now for this one here, I'm off to a great start. I need it to be a reactant, and it is a reactant. I need 1, and there is 1. It turns out this first given equation, it's perfect, just as it is. So if we rewrite the first equation, N2H4 liquid plus a CH3OH liquid turns into a CH2O gas, an N2 gas, and 3H2 gas. Wow, I almost ran out of page. And because I didn't make any changes, my delta H doesn't change. So it's a minus 36.8 kilojoules. All right. Oh, let's put a little blue box around our N2H4 liquid. Now, if we move on to our H2, here's my H2. We run into the same problem that we've seen in the last 2 problems. The H2 appears in multiple given equations. It shows up in the first given, it shows up in the second given, and it shows up in the third. Okay, it didn't have to show up in all 3 to be an issue. If a chemical shows up in at least 2 of the givens, then you really can't use it to modify your given equations. Right, so the H2, not really of any use to us. All right, so let's skip it. And we move on to the NH3 gas. So if I look through my given equations, I can see that the NH3 gas appears in only 1. Okay, it only appears in this one. Now the 2 questions you ask yourself, is it in the right place? And do you have the right amount? For this, it's yes on both accounts. You need it to be a product, and it is a product. That's great. You needed 2, and there are 2. Extra great. So again, this equation is perfect just the way it is. So I'm going to write it out. That's my N2 gas plus my 3H2 gas turning into 2NH3 gas. And my delta H doesn't change because I didn't change the equation. So minus 46.2 kilojoules. And let's put a nice little green box around the two NH3s. There we go. Now, just like in the last two problems, you have modified some of the equations, but not all of them. And in a Hess's law calculation, you're not allowed to just skip a given. Okay, if I give you 3 equations, you've got to use all 3. If you're given 4 equations, you got to use all 4. Right? Those equations are given to you for a reason. So because I know that I'm going to need it, I'm going to leave a space for it. But because I'm not exactly sure what to do with it yet, I'm just going to leave it out. Okay? So let's talk canceling. We know that there's not going to be complete canceling because not all of the hydrogen gases are going to cancel. Some of them have to be left. One of them has to be left, and it has to be left on the reactant side. So let's not focus on hydrogen. Let's talk about other things that are here that need to disappear. Let's talk about the CH3OH. If you look at your target equation, CH3OH is not in your target equation. This has to go away, which means it has to have a partner on the opposite side. So if I look here, so far, I don't have any CH3OHs, which means that the last equation is going to have to give me a CH3OH, right? Because there's nothing else here for me to cancel with. So if I want this to go away, it's going to have to come through the last equation. So if I do look at my last equation, it should have a CH3OH in it. If I look at it, it does have a CH3OH in it. Excellent. Oops, forgot my liquid. Don't forget your states. Now, it has the right number. I need one of them, and there is one. The location, though, is not right. I need it to be here on the product side, so that way they'll cancel. But in this equation, it's on the reactant side. So what I'm going to have to do is I'm going to have to take this and reverse it. If I reverse the equation, I have to reverse the sign. It was negative, it becomes positive. So if we rewrite it, the old products become reactants. So that'll be an H2 gas, and it's going to be a CH2O gas. The old reactant becomes a product, and I've already got it written down, right? That's how I knew where it was going to be. And the delta H, the number stays the same, 64.7, but it was negative and it becomes positive. Okay? By looking at what I needed to cancel and looking at something that absolutely canceled out, that there had to be none of it left, right? There's no CH3OH in this equation. That's how I determined what the last equation was going to do. Okay, so they're gone. Well, now let's cancel out the rest of our things. If I look at this, there's an N2 here, right? There's no N2 by itself in my target equation. So that means the N2 has the cancel. There's one N2 gas on the product side. There's one N2 gas on the reactant side. So they're gone. If I look at the CH2O, there's no CH2O in my target equation, so that has to go away. If you look on the product side, there's a CH2O. One of them and one of them, they're both gases. They cancel. Now, I did leave the hydrogens to the end because I know that the hydrogens are not going to completely cancel. Here on the product side, I've got 3 of them. Here on the reactant side, they appear in 2 different places. Right? There's 3 of them here and 1 of them here. So on the reactant side, I've got 3 plus 1 is 4. On the product side, I've got 3. So if I cancel out 3 and I cancel out 3, that leaves me with 1. And I do need to have 1 hydrogen gas as a reactant. So 3 hydrogen gas and 3 hydrogen gas. So if we write down what we have left, I've still got my N2H4 liquid. This is gone, this is gone, this is gone, this is gone, and I have an H2. If we look on the product side, canceled, canceled, canceled. I still have this, so 2NH3 gas, and this one's also canceled. If we look at what we've got left down here versus what we were aiming for, you can see that we have the exact same thing, right? We have achieved the target equation. So if adding these equations gives me the target equation, then I'm allowed to add up the delta h's. Okay, so the first delta h was a minus 36.8 plus a negative 46.2 plus a positive 64.7. That gives me a minus 18.3 kilojoules. This is the enthalpy change, the heat, that goes with this chemical reaction. If you're talking significant figures, 1 decimal place, 1 decimal place, 1 decimal place, so the answer has 1 decimal place. These are Hess's law's calculations, right? Hess's law says if you have a bunch of given equations and you can add them up to get a target equation, then you can add up the delta h's to give you the delta h for the target equation. These problems are a little bit more advanced because they do have chemicals that show up in more than one of your givens, and therefore that last equation is a little harder to nail down, a little harder to decide what you have to do with it. If you're still having trouble with these and it's more of the simpler background questions, like I said at the beginning of the video, there are 2 Hess's law calculation videos, number 1 and number 2. Number 1 goes over the basics. This one, number 2, deals with a bit more of the harder problems. So as always, thank you for joining me here at Chemistry with Dr. Clark.